is further very important theorem in vector calculus. In this video lecture, first we'll define what is Gauss Divergence Theorem. Usually it is called as a divergence theorem. We'll define this theorem, and then we'll do an example to have a verification of this theorem. So let's define it by defining its statement. Let f equals to f1i plus f2j plus f3k be a vector field where the components of f, say f1, f2 and f3, have continuous first order partial derivatives. That is, we have del f1 by del x, del f1 by del y, del f1 by del z, and so on for all the components f1, f2 and f3, and these partial derivatives are continuous. Now suppose there is a surface S, which is piecewise smooth. Piecewise smooth means differentiable. Piecewise smooth, oriented closed. It means the surface S which we have taken here, it is piecewise smooth and it has an orientation and it is a closed surface. And further, let n cap is unit outward normal to the surface S. So these are the preambles which we needed to define by defining a vector field, and we are ensuring the continuous availability of the first order partial derivatives of the components of the vector field. And we have piecewise smooth oriented closed surface S, and we defined unit outward normal to this surface S. Then what this Gauss divergence theorem says: flux of F across S that is F dot n cap d rho over the surface S. This is equal to the triple integral of the divergence of the vector field F over the region V, where this region V is the complete region enclosed by the closed surface S. So this is a very important result where we can actually evaluate the flux of F across a closed surface S via either this double integral, or the same flux can be evaluated by this triple integral. So this is how this is what we know this result as a Gauss divergence theorem. So now we'll do an example. Where we are going to verify this Gauss divergence theorem for a given vector field and a given closed surface. So let's take a vector field. F equals to xi plus yj plus zk, and we have a surface which is being created by an sphere of radius A, x square plus y square plus z square equals to a square. And we wanted to verify the Gauss Divergence Theorem, which says f dot n cap d rho over the surface S is equal to triple integral over the region V del dot f dv. Here you can quickly verify the preambles of Gauss Divergence Theorem, which we can easily check whether the Gauss Divergence Theorem is applicable on this example or not. So the first one is the components of the vector field f1, f2 and f3. They must have first order continuous partial derivatives. So they are actually the polynomials, so they are continuous and they are existing. And the surface must be piecewise smooth, orientable and closed. So since the given surface is here and a sphere, so it is a closed surface, and at every point on the sphere it has a unique outward normal, so it is orientable, and since it is continuous, so it satisfies all the clause to be applicable for the Gauss Divergence Theorem. So see, we need to evaluate the left hand side and the right hand side, and we wanted to check here whether both the values are coming out to be the same or not. If the values are coming out to be the same, then it will be a verification of the Gauss Divergence Theorem. So you can easily see the left hand side is nothing but the flux of F through this surface S, which is a sphere, this is what we wanted to evaluate. So F is with us, n cap, we can define the equation of our surface, which is already given, x square plus y square plus z square minus a square. Now we can evaluate our unit outward normal on this surface S. This is going to be gradient of g divided by its absolute value. So gradient of g will be 2xi plus 2yj plus 2zk divided by 2 times under root x square plus y square plus z square, and this will be equal to xi plus yj plus zk divided by, we know x square plus y square plus z square is equal to a square, so this will become under root a square, which is a. So this is our unit outward normal n cap on any point on the sphere S. Now we are in a situation to evaluate the surface integral, means left hand side, LHS. So double integral over the surface S, f dot n, we can separately evaluate it. F dot n will be, this is going to be x square plus y square plus z square upon a, and this x square plus y square plus z square is a square, so this will become a square upon a, which is a. So f dot n ds, sorry, this is d rho, this is going to be double integral over the surface S. F dot n is a d rho. Now to evaluate this surface integral, we need to take the projection of this surface in any one of the plane. So if you take a sphere here, and suppose this is x-axis, y-axis and z-axis, and if you take the projection of this sphere into xy plane, it will be a disk of radius a. So let's take its projection into xy plane. So this integral will be equal to integral over the region R, where R is x square plus y square equals to a square, and this a d rho will be the value here, mod del g upon mod del g dot k cap dx dy or dy dx, whatever we wanted to put. So del g we have evaluated. Mod del g will be double integral over the region R. Mod del g will be under root 2 times under root x square plus y square plus z square, which is 2a, and del g dot k cap, this will be equal to 2z. So let's put these values in this integral, and we will get 2a dot 2a divided by 2z into dx dy. So let's evaluate it. This 2 cancels this 2, and let's take a square outside the integral. A square double integral over R 1 upon 2z dx dy. Now let's put the value of z here. The value of z is 1 upon, this 2 is not here, under root a square minus x square minus y square dx dy. We can solve this integral simply by converting this integral into the polar coordinates, and this region is R, which is a circle. So once you will solve it, its value will come out to be 4 pi a cube. It's not a challenging integral. You can simply solve it by converting it into polar coordinates, and the limits can be put for a disk whose radius is a. So this 4 pi a cube came out to be the value of the left hand side, which is double integral f dot n d rho over the surfaces. Now let's come on the right hand side. So for right hand side, what we needed the divergence of f. This is the right hand side of the Gauss Divergence Theorem. So let's first evaluate the divergence of f. The divergence of f is going to be 3. So let's put the value of this divergence of f into this integral over v 3 dv, and here this v is actually the region which is enclosed by the given surface. So in this case we have a surface as a sphere whose radius is a. So this entire inside region in this sphere is going to be our region V. So this can be simply evaluated 3 times triple integral dV. If you carefully see, this is nothing but the volume of the sphere. So 3 times into volume of the sphere is 4 by 3 pi a cube, which turns out to be 4 pi a cube. So in this case here we saw the LHS came out to be equal to the RHS, and this completes the verification of the Gauss Divergence Theorem. While using the Gauss Divergence Theorem, we have to be very sure about the closeness of the surface, because we can use this Gauss Divergence Theorem in the case only when the surface is closed. If the surface is not closed, this approach may not be applicable.